Any other questions? All right, thank you.
Thank you, Tina and Kyle. Our next speaker is Dr. Brent Auvermann. He is the Center Director for Texas A&M AgriLife Research and Extension Center. In Amarillo, Dr. Auvermann's extension and research programs involve environmental quality, including air and water pollution. He is also a faculty member in the Division of Agriculture at West Texas A&M University. Previously, Dr. Auvermann was a USDA Fellow in Water Science at Colorado State University. He has authored more than 30 publications, papers, and reports on livestock manure management, odor, dust, and water quality. Please welcome Dr. Brent Auvermann.
I'm going to have to get some new introductory remarks. The ones I keep sending in sound less and less glamorous every time. Thank you very much for the introduction. They're going to do a little bit of technological wizardry at the back. I'm going to spend just a few minutes today talking about drones in agriculture, and I'm not going to cover things at a minute detail, but I want to give you an overview of the regulatory landscape for drone use in agriculture. Spend a little bit of time talking about our research program at the Texas A&M AgriLife Research Center there in Amarillo, here in Amarillo, and then I'll spend just a couple of slides talking about the commercial uses and the possibilities that we have. So let's see, there we go. All right, so regulations, a little bit about our research, a little bit about commercial opportunities, and a few things that we need to be wary of when someone comes to us wanting to fly their drones over our property. The federal government, the Congress, in fact, gave the Federal Aviation Administration a mandate some years ago to integrate unmanned aerial systems, or UAS, you and I, we'll just call them drones if you want to, integrate them into the national airspace. And the idea was, look, we want FAA to reduce the barriers to commercial entry into the airspace, streamline the requirements, preserve, and do all of those things while preserving public safety and security. Now, I'm here to tell you that whenever I hear that Washington is about to do something, I take a step back. In this case, what they have done has been phenomenal. And it has really liberated up an important piece of the commercial opportunities in the United States. So before August of 2016, the opportunities to fly commercially, and by commercially, we don't mean just for money. We mean in the process of enterprise instead of just being hobbyists. If I'm farming, for example, if I were farming and I decided to fly a drone over my fields to help me make decisions about how I'm going to farm, then that's engaging, in my opinion. I would opt to interpret that as engaging in the commercial use of drones. And so anything that I say about regulations that pertains to commercial use of drones, I hope that you'll take that suggestion to heart. One of the things we definitely don't need is for the rather liberal possibilities that we've been freed up to do a lot of things. We don't want to lose those opportunities because there was a lot of people getting into mischief, flying drones when and where they shouldn't have been. So going through the process of getting certified, et cetera, is a really, really good thing. It's an important thing if you're going to be engaging in the use of drones in any commercial way. Anyway, before August of 2016, if you wanted to fly drones commercially, you had to do so within an area that was designated with a certificate of authorization. You would hear people talking about COAs. Well, there was a COA down on the Texas coast that covered many, many hundreds of square miles right there along the coast, associated with Corpus Christi and all the aviation that goes on down there. And then we, for a couple of years, we had a COA that overlaid Amarillo Canyon almost all the way down to Vernon. And you could fly in that area if you had a certified pilot. But at that time, it wasn't necessarily a drone pilot having a special certification. You had to have a pilot to do your piloting for you. As you might have imagined, or as you might imagine, that was going to be a very expensive proposition. On the research side, if we had wanted to fly drones in our COA, I couldn't have done it. I would have had to hire some of our colleagues from Corpus to come up here, do the flying for us, and then provide the data to us. And by the way, as you know, the Texas High Plains, the weather is not always predictable 2 weeks out, as people's travel schedules require. So the whole thing, COA, was a great idea, except it didn't work. It didn't work for us. And it didn't work in areas where you needed somebody to be nimble and responsive to conditions that would allow you to fly when you wanted to take advantage of it. August 2016 changed the game completely. We'll call them the Part 107 rules, and I don't want to go into too much detail on exactly where you would find that in the Federal Register. But let me give you a little primer on the Part 107 rules. First, now we have a classification called the Remote Pilot in Command, RPIC, and the guy you see there, notice he's leaning backwards. He's using body English, trying in vain to get that drone to land on that orange spot. But anybody can fly, as long as they have the certification for drone operations. Well, 7 of us at the Texas A&M AgriLife Research Center, along with one of our USDA colleagues with the Agri-Search Service, went in last April, took a class, took a test, bada bing, bada boom. A month later, I have my certification card, and I can fly anywhere within the rules. I don't have to fly just in an area designated with a COA, or with a Certificate of Authorization. So I do have to obey the rules, and I'll detail some of those rules here in just a minute. The training process, if you're interested in getting into this game as a consultant, the training game is there's really a cottage industry that has sprung up around training people to get their remote pilot certification under the FAA. And so when I tell you that back in the olden days you had to go in and take a class, recall that the olden days was about a year ago in this technology space. Anymore, you can get the education you need done online, and of course the exams have to be taken in a secure way so that you can't send somebody in there to take your test for you. All right, I'm looking at you, right? Of course, there's laws, regulations, rules, and maps covered in the training. And in just a minute, I'll show you those. How many of you are pilots already? I know we have a few in here. There's a couple of pilots. You know what picture I'm fixing to show, right? I think it's next. It's not next. Let me go to it. There it is, right there. Have you ever looked at one of these? I think this is called a sectional map or something like that. Sectional map. There's more going on here than any one person ought to be able to understand. And thank God this is just Amarillo. Lord help you if you want to fly a drone anywhere within 20 miles of Dallas-Fort Worth Airport. There's too much going on. But the point is that during this FAA certified training, you learn how to read these maps in order to determine whether or not the place that you're about to fly is within a certain distance of an important airspace. Drones are allowed to, under Part 107, are allowed to operate in what we call Class G airspace, and I'll get to that in just a minute. But the drones we're able to fly under Part 107 are drones that weigh less than 55 pounds, including the payload. Now, if you've been out back here at the USDA ARS information desk at their booth, you'll see a hex rotor or a 6-rotor UAS that we and USDA will be using together to do some water-related, irrigation-related research. I encourage you to stop by and take a look at what a hex rotor looks like. You can also get octocopters, which are slightly bigger even than that, all the way down to quadcopters. You'll notice they're all multiples of 2. And that's because we want redundancy in these things. If you have a rotor spinning this way, you need another one spinning the opposite way, or that thing is gone. So there should always be an even number of rotors. There are also fixed wing platforms. I'm not going to say too much about those, except in passing here in a few minutes. And then on occasion, you'll find that one of the technologies you'd like to put up on a drone as a payload is technology controlled, which means we don't want ISIS getting their hands on it. So advanced thermal cameras, for example, those have military uses and nefarious uses. And so if you want to hang a high-resolution thermal camera underneath your drone, you're going to have to deal with the State Department as well as the FAA to make sure that that technology is controlled and not exported in any way, either the platform itself or the data, or the computer that the data are stored on. Anyway, you probably don't have to worry about that too much. It won't be long, I think, before technology advances to the point where we'll be able to afford to do things with technology that is not export controlled. So where are we able to fly? Class G, uncontrolled airspace. This is airspace that you don't hear a lot of radio chatter about it because there aren't towers there in general. And what we're trying to do is stay at least 5 miles from the nearest airport. We always have to fly with the drone in visual line of sight by the pilot, not by friends and helpers, but by the pilot, him or herself. Visual line of sight only. And in most cases, Class G airspace, the part that's available to us for drone operations under Part 107 is below 400 feet above the ground, or above ground level. Only during daylight hours. Now, those of you who hunt, you'll be glad to know that the daylight hours for Part 107 drone operations coincide with the sun-up to sundown hours that you're used to hunting. 30 minutes before sunrise, 30 minutes after sundown. It is possible to get a waiver to fly at night. I don't know what the specific requirements or difficulties are associated with getting a waiver like that, but it is possible. It's even possible to get a waiver for some of the other requirements, like below 400 AGL. So waivers are possible. I haven't been down that road, and I wouldn't be able to answer any questions about it, except I would just say, be ready for a little extra bureaucracy. Now, flying the drone is only part of it. In fact, we use the term UAS to refer to the bird plus the sensor plus the operator plus anything else that's being used to make sure that that mission is successful. That whole thing constitutes the unmanned aerial system, or UAS. The sensors that we have available to us are getting more and more sophisticated almost by the hour. The first one that you're going to be most familiar with, I've put in shorthand as RGB. That's really nothing more than a digital camera like the one you have on your cell phone. Red, green, and blue bands, and put those together and you get a visual picture. So those kinds of images would be the kind that you see on your cell phone when you take a picture of or a selfie. Another kind of sensor type is multispectral. When you hear someone talk about a multispectral imaging platform, they're talking about one that probably has R, G, and maybe B, that is the visual bands, red, green, and maybe blue. But they also are going to have at least one and maybe two or more bands that are not bands of the spectrum that are not visible to the human eye. In most cases, they're going to be red, green, and blue or not, and infrared, and something between red and infrared, which they call red edge. It's usually a 4 or 5 band sensor, and there's information in those infrared bands that can't be picked up with the naked eye, but can be used to develop some very important metrics about the growth status of plants, for example. So multispectral is really where most of the work is going on right now in the use of drone-mounted remote sensing over agriculture. Hyperspectral, if you imagine multispectral just put on steroids, and instead of having 4 or 5 bands of the of the spectrum available to you. Hyperspectral cameras are often programmable to the point where you might be able to gather 100, even more than 100 individual bands within the individual slices of the radiomagnetic spectrum. Hyperspectral cameras are capable of reading across the entire spectrum just about, and you can program them then to take the slices that are of interest, where the information lies that you're interested in. They also generate enormous data files. So, for example, the drone that's back at the USDA table, or a drone exactly like it, will be carrying a $60,000 hyperspectral camera on it, and it will be generating not gigabytes, but terabytes of data, nearly terabytes for each flight. So, if you've got a computer that can handle that kind of stuff and you've got some disposable income on the order of about 6 figures, I encourage you to jump into the hyperspectral space, be ready to deal with the State Department on some technology control. But there's a lot of information outside the electromagnetic spectrum where you and I can see. Infrared, ultraviolet, even beyond. Another sensor that we're going to be using fairly widely and is probably the next frontier for agricultural-related work is the thermal band. I already mentioned that some of these thermal sensors are going to be export-controlled, but the idea is this is way out in the infrared spectrum, what we call long-wave infrared. And when you see pictures, thermal pictures of a house, for example, you're looking at a thermal image. These are a little bit more expensive than your ordinary camera, digital camera. And because they're more expensive, when you pay $1, you get lower resolution thermal than you would for an equivalent amount of money spent on an RGB camera or a multispectral camera. LiDAR is an interesting, if you've ever heard news stories about drones being flown into some building after an earthquake, a LiDAR is probably mounted underneath that drone, and it is spinning and shooting a laser beam at everything that it will hit, 360 degrees, spinning very fast, moving up and down, and what it is building is a point cloud so that you can see what's inside the building without having to go inside the building. Amazing technology, and it can be used to very good effect in agriculture. If you can fly these drones down near the canopy and map the canopy in very high resolution and see individual leaves. You can probably see individual aphids if you have the right, on the underside of the leaf, if you have the right resolution LiDAR. LiDAR is extremely powerful technology, and it's really the light analog of radar. You send the beam out, it bounces back, and you determine how long it took for that beam to go out and back, and you do some fancy calculations, and it tells you what's out there. There are many other sensor types that are in development. In my work in feedlot dust, for example, we'll be mounting a dust sensor on a mast that sticks 4 feet up above a UAV, and I'll be flying those around to measure the concentration of dust in a plume, for example. Lots of other possibilities on this platform. It's almost an inexhaustible platform for interesting things. They may or may not be useful. So in agricultural research, what are some of the uses for these things? First, the first and most obvious one to us was in plant breeding and comparison of different varieties. We have a wheat breeding, one of the world's best wheat breeding programs at the Amarillo Center and out at our Bushland station. And we have begun within the last year flying our wheat variety plots, and it's amazing to see from above what these different varieties are doing even just after they've germinated. We have some dryland wheat out on the west side of the joint USDA AgriLife facility in Bushland. It's dryland wheat, several hundred varieties, and early on we had so much fall moisture that stuff sprouted right up. And then the spigot turned off, and we're finding out by default which of those varieties is most drought tolerant just by flying over them. And it's easy to see even early in the growth stage. So we'll be mapping the growth stages of these different cultivars as they grow, and coming up with some conclusions about what we could determine early enough in the season for you to do something about it as a farmer. Disease and pest detection is another obvious one. Many of you have seen the effects of, say, wheat curl mite or wheat streak mosaic virus on wheat. You'd be able to pick that up easily within overhead imagery, not only in the RGB, where you'd be seeing yellowing, but we might also pick it up in the infrared portion of the spectrum as well. So disease, pest detection is I would call it low-hanging fruit for UAS operations. Of most importance, perhaps to y'all, can these devices be used to plan irrigation, to track soil moisture? The answer is probably yes, although it's hard to see below the surface of the soil. That's a nut that nobody has yet cracked, and that is how to see from 100 feet up what the soil moisture is at 18 inches. So there's quite a bit of work yet to be done there. I'm not sure that part is going to be successful, but there's a lot of stuff that we can do about the soil surface and about the plant as an indicator of moisture stress. There ought to be things that we can pick up, if not in the RGB bands, at least in the multispectral bands. My research team is using drones in agricultural research to identify areas where greenhouse gases are being emitted most rapidly. In most cases, that's going to be where it's wet. And don't want to get wrapped around the axle on the details of that, but I'll show you a picture here in just a minute. And then finally, as we get better and better at resolving temperature differences within a thermal image, I think we ought to be able to detect the health status of livestock. It's going to be harder during the day, especially with very dark cattle, for us to do that, especially in the summertime. But I think flying either in the evening before the sun goes down or immediately afterwards, we ought to be able to start picking up some thermal differences within the animal that would give us a signal that perhaps that animal has not gone off feed yet, but we may be seeing the signs of some clinical issue emerging in that animal. This is a picture of Dr. Jordan Bell's forage sorghum plots east of Bushland High School. This was taken in September of 2017. And as you can tell, there's a tremendous, we're looking straight down here, there's a tremendous amount of variation between and among forage sorghum varieties. And what's really amazing now is that even without a LiDAR, one can take a series of images like this as the drone flies over and recreate the structure of the sorghum plants using a routine called structure from motion. That is, we're taking the same picture, taking the picture of the same plots from several different angles as the drone flies over, and we're able to reconstruct the plant height, the vegetation density, et cetera. It's amazing technology, and it's going to be in your hands before you know it. This is an overhead picture down here in the middle. That's an overhead picture of our experimental feedlot at Bushland, Texas. That's a portion of it anyway. We'll be doing some work there looking for greenhouse gas emissions. On the left-hand side of your screen, you see a picture of 6 different simulated feedlot surfaces. They're big steel pans filled with dirt and then covered with an inch or two of feedlot manure, and we're wetting them up and measuring greenhouse gas emissions from them and using thermal imaging to measure the temperatures, the various temperatures. If you look at the back left of those six pans, you'll see a couple of concrete tiles, one of them painted white, one of them painted black. Those are our reference temperature tiles, and those are the 2 tiles that are shown in the upper right-hand thermal image. Turns out that the black one in that image is actually white because it's colder, and the white one is actually black, is the black one, and it got very, very warm during that July day. Anyway, we'll be using thermal techniques to try to identify hot spots, as it were, for greenhouse gas emissions from the feed yard surface. If you look really closely, you'll see a little white square. Many of you who do forage surveys on pasture land will throw these kinds of frames out there randomly across the countryside and then go in and clip the forage that is within that and get an idea of what the pasture biomass yield is, how much livestock how many livestock will that acre of ground support? Well, we'd like to be able, instead of throwing a bunch of these squares out there and taking 3 or 4 people out there and clipping forage and weighing forage, drying forage, and then weighing the forage again, and we ought to be able to just fly a drone over there and get a very good estimate of the forage yield, and we ought to be able to do that weekly and give farmers and ranchers an idea of what the pastures will support at any point in time. This is cotton. Have you ever seen red cotton? This, every red blotch there is a cotton boll. And it's not because the cotton itself is red, it's just the image processing software that our colleagues at Texas A&M Corpus Christi put together to measure the number of bolls in a particular area. And then they color-coded them red so to be able to see them easily and so that the machine would be able to count them. It's amazing technology for yield prediction. So if you wanted to know whether or not you were likely to make a bale and a half of cotton and the bolls have just opened, you might wait a couple of days and then fly that field and then run the images through this process that Corpus Christi has developed and spit out an estimate of what your cotton yield is likely to be. So we've got 7 pilots at our center. We've got 7 multi-rotor drones in our fleet. We're using only those 4 sensors at the moment. I can't afford a LiDAR just yet. We're working on it. We also have to have a survey-grade GPS so that we can get really, really precise measurements of exactly where we are. A bunch of gee whiz stuff that goes into this. So yeah, you can fly a drone, but as I'll say in just a minute, as I wrap up here, well, I am wrapping up. Getting the images is the easy part. It's what you do with them later that becomes the real challenge. So selecting your drone, the multi-rotor flies low and slow comparatively. You're likely to be able to cover smaller acreages with it, but get very high resolution and low blur, very distinct pictures. Fixed wing aircraft can fly higher and faster, fly longer missions because the power to weight ratio is much higher. And as a result of being able to move fast from a high elevation, you'll be able to get large acreages relatively efficiently. So my guess is that over time, because sensors will always get better, the holy grail of all of this is being able to fly a fixed wing rather than a multi-rotor. A multi-rotor is they're useful now and they give us really high resolution stuff, but boy, for $1, I'd rather fly a fixed wing to get more data per dollar spent. So what are some uses in production agriculture? Of course, precision agriculture, trying to find out what areas of the field I should invest in and which areas of the field I can abandon or should abandon in order to improve my bottom line. Pre-harvest yield detection, as we've already talked about. You can fly these up and down an irrigation system and determine whether or not you've got nozzle issues here and there or a hole in a drop hose. Pest, stress, and damage scouting is going to be a really, really excellent application of this, especially when the research matures and yields some off-the-shelf algorithms that can be used to process images for that kind of information. Of course, those of you who have livestock and or wildlife interests have probably already entertained the idea of getting drones to help you ride your North 40. And then finally, logistics, and I don't even know where to start with the logistical possibilities. Last slide, word of caution. And images by themselves are just pretty pictures. And the goal in all of this is to come up with some kind of actionable intelligence. You don't want to be spending money on a bunch of images. What you're spending money for, I hope, is for information that you can use to improve your bottom line. And that's not as easy to do as it is to say. And so I guess I would caution you, be careful. Ask questions, and if we can be of any help to you in trying to figure out how to integrate UAS operations into your enterprise.